going to first take you back in time. And if you will look at the history of humankind, each time we had to give a name to a specific period of our history, we used the name of materials, in fact. We had the Stone Age, the Iron Age, the Bronze Age, and all these things. And even the Industrial Age is known as the Steel Age, in fact. Now, I like to say that what we are living right now, it's the Materials Age. And the Materials Age has got two main challenges. We are faced with the challenge of sustainability and equity, which is very important for us. And we are also working, I'm looking at my time, we are also working in the Materials Age at, I will say, the frontiers of disciplines, and also within the convergence of discipline. I like to say I used to be a polymer chemist when I started, but now this has evolved, because if we don't evolve as scientists, we don't apply what we do, because the discussion earlier we had on AI is very important, because we have problems to solve and we have to evolve with that. And again, let's move from the Silicon Valley to the Great Rift Valley. We have to bear in mind that during the Stone Age, the first tools of humankind came from the Great Rift Valley, which is not very far from here. And the first composite materials that we had came from Southern Africa, almost 100,000 years ago. Therefore, this is the question of Africa in material science and engineering. And where is nanomaterials in all that? I will just take one example. In Egypt, a long time ago, they used to use dye for hair, and a recent study which was done to analyze this dye, it was used in the exact same condition, and they found that this dye in fact contained nanocrystals of lead sulfide, and this could penetrate the complex structure of the hair, which is a biomaterial, and could accumulate. And this has been proved by SEM and EDX images. Therefore, nanomaterials was there, but we couldn't explain what they were. We didn't have the tools for that. And I'm in tissue engineering. Where do I find the first examples of that? In museum. You just go to museum, you will find that animal bones, teeth, corals, metals, all these materials were used to replace missing bones, teeth. Therefore, this is the history of material science and engineering, and Africa is very much linked to that. And when you have material science meeting nanotechnology, you have powerful tools for radical change. Now, I will say that all these challenges are organized around four main axes. We have health, we have energy, food, agriculture, and of course, we have smart manufacturing. And putting nanotechnology in those four axes, we can do wonderful things. Now, in our materials age, everything that we have as challenge is aligned with the SDGs, the UN SDGs. And the UN SDGs is not only a problem of developing countries, because we all live on the same planet. Therefore, it's both developed and developing countries. And we have to work together with that. And today I'm going to concentrate myself on healthcare, because this is my area. I'm going to try to use some examples of things that we have done, of networks that we have built, and how these networks are enabling us to do things. At the center, we have organized, our center is very young, that is, we started the center in 2011, and we had to trade off. We had to leave our faculty and accept to be at the center and build everything. We have our PhDs, our postdoc, then we have our research first, and of course, we need industry to uptake everything that we do. Therefore, we have strong links with industry as well. And by so doing, we operate really at the frontiers of science, engineering, and medicine. That's why I say I started as a polymer chemist, but you have to get into the engineering. And therefore, it all started with chemistry. I remember I had a very big debate with a mathematician, because we said that chemistry was a central science. He couldn't get it. Central science, it's because it links. It links the physical science with the applied science. It's not because it's the most important science. And that was the debate. And with chemistry, because we are into tissue regeneration, we have to understand what's going on there. The cells, they are surrounded by biomaterials. If you don't understand the biomaterials, you can't make tissue engineering scaffolds to regenerate this tissue. And tissue engineering scaffold is also a way of reconciling modern and traditional medicine, because traditional medicine has been something which has a lot of importance on the African continent, but this is a way where we can merge this knowledge into modern medicine. Now, we started with wound healing scaffolds, in fact, but we moved on to using this knowledge to 3D tumor models, to cancer regenerative medicine, cell encapsulation implants, nanofiltration membrane, and now into innovative textile. All this using our prior knowledge in tissue engineering scaffolds. And how do you do that? I mean, you have to understand things that are going on into two disciplines that we as humans, we consider as separate, but they are not separate. That is, we have to be able to understand the knowledge traffic between biomaterials and understanding science. And how do we do that? Once you understand that, what do you do with that? This is where the engineering comes in. That is, it's the science and the engineering working together. Now, I will give to you a few examples of the scaffolds that we have made. This one is piezoelectric scaffolds that we have. And the good thing about this scaffold is that it gives scarless tissue regeneration. There is no scar. We have tested this many times on in vivo model. And why is it called piezoelectric scaffolds? Because when the cells move on these, they produce electricity. And it is that electricity that is going to promote the good aspects of the cells that you want to see. And this is one type of scaffold that we have made. And in fact, we make these scaffolds for difficult to heal wounds. And we started off with diabetic wounds, but later we found that this could be used for other types of wound, particularly this one. This one is another type of scaffold. It's an injectable hydrogel scaffold. It's basically made in 2 steps. You've got 2 solutions in water, you mix them, you get your injectable hydrogel scaffold. This is the nice thing about the scaffold. And it's self-healing. That is, once it's in the wound, and let's say the scaffold breaks itself under pressure when you stand up or you sit for a long time, the scaffold has the ability to heal itself. Therefore, you don't have to intervene on that scaffold. And also, you must have heard of diabetic wounds that reopens. They don't heal. It's because the quality of the tissue that you regenerate is not good quality. And this scaffold, in fact, gives good quality tissue. And this is going to encourage wounds not to reopen. And in fact, when we have done some clinical studies, we've seen that when the wound reopens is because when the person is going to stand for a long time or sit for a long time, you put a lot of pressure on that new tissue, which is the tissue is not able to sustain. Now, we were, when I talk of wound, we were in skin wound. We moved to bone regeneration. This is the model that we used. And this is our first collaboration that we had. In fact, Mauritius is close to Réunion Island, which is a French department, and they have an EU animal facility level 2. We can even do infectious diseases as well now. And this collaboration, because these people, they are specialized in vivo on animal studies. This is where we brought our expertise together and we started looking at the problem of wound regeneration. And we came up with a very nice scaffold. And these are the results, just preliminary results. We found that our scaffold on this model is performing much better than a medical device which is being used in clinic, which is basically collagen and hydroxyapatite. And it's giving very nice results, not only in terms of regenerating the bone, but it's how you fuse the old bone with the new bone, because you don't want the new bone to break up under any mechanical tension. That is, there should be a good fusion between the two. And this scaffold is giving this type of results under the CT scan. It's the quality of the bone which is important. Now, since we are in biomaterials, we are an island, we have millions of kilometers of sea at our disposal. We look at marine natural products. And this is one material that we have been using from a coralline algae, and we have added it to our bone regeneration scaffold, our piezoelectric scaffold, and it's giving nice results. One thing I want to point out is that when we do in vitro culture, we do not do single cell in vitro culture. We try to imitate what goes on in our body. That is, we do multi-cell in vitro culture, more than one cell, because we want to see how they interact with each other. This is this is our own models. That is, we have developed these models ourselves. And by putting all these cells together, you need to have the correct conditions to grow them. You want both to grow. You don't want one to grow and one not to grow. You try to mimic it. And it's an inexpensive way of doing things before going to in vivo. And these things are possible. And we have a good collaboration with the WITS Advanced Drug Delivery Platform. And Prof. Yaya is here as the director. And now we are looking at going further with these marine natural products. And we are looking at all the problematic of cancer. I was very happy to see the AI image classifier, because we have done something on something else, but a bit similar. And this collaboration also has the Mauritius Oceanographic Institute. So we have isolated one family purified compound, and it has been tested on a number of cell lines. And now we are looking into putting them into scaffolds. And why do we want to put them into scaffolds? Because this is something when I remember I discussed this idea some 3 years ago with a collaborator from Australia. Nobody called that cancer regenerative medicine. And we started by writing a review, because we have to understand what is cancer regenerative medicine. And I'm very happy to say that we are the first to have started working on that, because when you have a tumor, you remove the tumor, it's a wound, it's a tumor, it's a wound. You have to heal that wound. But you want to heal that wound without making the cancer cells that are residual come back. It's very tricky. And as material scientists, you have to be able to come with a good scaffold that's going to promote wound healing and not encourage cancer cells to grow. And only the materials of the scaffold allows us to do, you will see cancer cell migration on the top, and the cancer cells do not even migrate on the scaffold, because the materials we have chosen are like that. And whereas the fibroblasts, which are very much responsible for tissue regeneration, they are very happy on the scaffolds. And with Yaya, we are looking at the in vivo studies, and we are going to test this. I mean, the mice model already. We're going to test them on the scaffolds on these mice models. And we went further. We saw that just having 2D culture for cancer studies is not enough. And we have available scaffolds, hydrogels, nanofibers. We can do anything as material scientists. We can work on the physical chemical properties and get any type of structure. So we've been studying 3D models that people can use. In fact, cancer cells, they are mostly surrounded by fibroblast cells. These fibroblast cells, they tend to protect the cancer cells and create drug resistance and things like that. So we are building spheroids made up of fibroblasts and cancer cells. So other people can use that for drug screening. We're not going to do the drug screening, but we can make these types of things for people. And this is our most recent thing, and it's also a collaboration which we started with Max Planck Institute of Medical Research. My postdoc is here, and she's just coming back from Max Planck. We want to do cell encapsulation on our hydrogel scaffold. The final aim of this cell encapsulation is to be able to have subcutaneous implants for insulin production. So if people have problems with insulin, we have those scaffolds with the required cells. These cells, they are pancreatic islets. They can build up blood vessels. They produce insulin, and the insulin can go into the bloodstream. This is the final aim. And we want our injectable scaffold. When you inject the scaffold, you have cell encapsulation and hydrogel formation in one go, so that the implant is not a painful surgery. It's just by an injection. This is our final aim, and we just started this collaboration with Max Planck. At day 7, the cells are still alive. They are growing in the implants. Now, we've been talking of AI, machine learning, and we also saw that this is a problem. The problem we have, cell-material interaction, could be solved by using AI. I always like to argue with my colleagues in AI to tell them that AI is a tool and you need to solve problems. And this is one problem which we've been looking at. And first, we looked at cell-material interaction. This is published. Second, we are looking at the material-material interaction, because we want to influence the properties of the scaffold. And third, we are working on an image classifier for our macrophages. Macrophages are responsible for inflammation. If you have bad inflammation, there is no tissue regeneration. And we want to be able to detect the different phenotypes of the macrophages and then predict what this scaffold is going to give in terms of inflammation. And this manuscript is underway, and Lakshmi, in fact, is going to go into the group of Kelly Chibale to do more machine learning. And COVID allowed us to review many strategies. I like to call this spin-off knowledge, because we just don't do science for the sake of doing science. We want to solve problems. We have so many things available, all these nice scaffolds, we can do so many materials engineering, but we want them to be useful. And during the COVID pandemic, I just met the CEO of a textile company who happens to be an engineer as well, so we understand each other. We came up with a nanofiltration membrane using our scaffolds. The problem is that you need good breathability and good filtration. And this nanofiltration membrane is fully washable. I use them. It's in the mask, and it's certified in the US, FDA certified. And we've manufactured for the campus during the COVID pandemic. And now we are into high performance compression wear as well. There is a study underway with athletes. We are testing this to see how they can recover after efforts. And all this, they are spin-off knowledge of materials engineering. And I told you earlier that Mauritius may be a small island, but we have 2.3 million kilometers square of sea, which means huge marine resources. And we are looking into the circular economy with industry. And just now we have upscaled the extraction of collagen from fish waste. And the yield has gone from 3 to 25%, which is a good thing for industry. And this is how we work with our industry partners. And what is the future? No materials on its own can mimic the complexity of things that we want to do. Innovative materials blending is very important for us to look at, because we want the material to be able to evolve with the tissue as well. And this requires really work at the frontiers of science, engineering, and medicine. You have to be able to understand that. You need a team that can understand, can bring their expertise in that. And also you can expand the knowledge to other areas. I've shown to you nanofiltration membrane. And what we really need is support for materials engineers and scientists. I'm not talking of projects that are for 1 year or 2 years. I'm talking of programs. I mean, those that are already working in this area, they need funding for programs so that they can keep postdocs, they can keep this type of expertise and continue to work with collaborators. This is what we need. We need long-term programs, which could be co-chair. Since we are at the US-Africa Frontier Symposium, it could be co-chaired by somebody from the US and somebody from Africa. These are the type of things that we need. In June of this year, we organized a discussion with Prof. Langer. And Prof. Langer is a very nice person because he likes to give advice. And we discussed about what we can do in this region of the world. And there are a number of things that came out. And he, of course, he presented his experience and on Moderna, Momenta, and Zymeworks. You all know about Moderna vaccine. And the early investment in spin-off is very important. And we don't have that type of structure yet in this part of the world. And what is the human capacity what we required in there? And most important, we need to create a great culture. Without this great culture, we will not move forward. That is a culture of always asking questions, always getting into networks, always discussing with people, even if they are not in your area, because you get good ideas. And nothing would have been, nothing is impossible without a great team with a great culture. Now, this team that we have, it's 70% women. And we've got a good network, and we've got good industry collaborators. I'm happy that they are themselves engineers, so they understand what they want. And I would like to thank Samuel, because he's doing a great job at AMRS, our networking people together. And I would like to finish with this. Since we are at the US-Africa Symposium at Frontier Science, nothing is impossible.